Hello, my name is Robert Labs. I'm from University of West London in England. I'm here to present a paper titled Echocardiographic Image Quality Assessment using Deep Neural Networks. What is echocardiography? Echocardiography, otherwise known as cardiac ultrasound, is the imaging modality used to assess the structure of human heart and its cardiac functions. Cardiologists around the world rely on echocardiograms to detect all forms of heart abnormalities. During transthoracic clinical examinations, the diastolic and systolic functions of the heart can be quantified to determine how healthy a heart is. And because of this, echocardiography becomes a preferred imaging modality compared to X-ray, CT scan, or MRI. Another reason is that it offers exceptional advantages of a non-intrusive, non-ionizing, low cost of ownership capabilities. And therefore, it is mainly used for transthoracic examinations and during the point of care services. Nevertheless, it poses techno-clinical challenges. These challenges implicitly impair reliability and diagnostic outcomes. The problem with echocardiography, however, is the image quality. The way the images are produced through interference pattern of scattering centers inherently has poor resolution. The images are not well defined. For example, the image on the center of my screen, highlighted with the laser pointer, represents the photographic image of a sliced heart. This view produces 4 clear chambers. They are labeled right ventricle, left ventricle, right atrium, and left atrium. However, the image beside it is the 2-dimensional echocardiogram, which represent the 4 chambers as well. Now, this quality of images is inherently poor, and the operator's experience also counts. The typical image quality samples that we've come across in these studies are as follows. The first one is the poor quality. And you can look at it, the chamber here are highly indistinguishably recognizable. The next one is the average quality that shows the cavities, but they are not having well-defined edges. The third one is the optimum quality, which is the target of every operator and cardiologist. This is because the reliability of echocardiogram depend on the quality of images acquired. High quality yield better quantifications and accurate diagnosis, while poor quality images yield inaccurate measurements and misdiagnosis. In order to ensure that operators and cardiologists quantify optimum quality all the time, certain clinical standards are therefore put in place. One of such standards is subjective assessment. The subjective assessment procedure allows the expert to evaluate each cardiac images and determine their clinical relevance and suitability for measurements. This process in turn is a high-cost venture, and it places pressure where short expert skill is required. Reliability issues and poor trigger response also comes as a result of subjective assessment. Now, the way around this is to go with objective assessment. However, there are 3 main issues that needs to be resolved in order to implement objective assessment for cardiac frames. The first one is there is no availability of cardiac images in public domain, because cardiac images are highly personalized and are protected by General Data Protection Act 2018. So an ethical approval is required in order to conduct a study. The second problem, however, is that there is no generalized, coherent objective standard defined for two-dimensional echocardiographic images. We have to come up with one. Lastly, it's unclear to experts what constitutes the quality of element with respect to different pathologies and varying patients' needs. In our studies, we adopted a methodology where we obtain the cardiac data set for our study. Also, we made expert consultations. The consultations is in regard to what are the features paramount to cardiologists, paramount to clinicians, paramount to operators, and we're able to have the rating based on visual assessment, the quality rating for each of the cardiac frames we obtained. The rating is from 1 to 10, and 10 being the best quality, 1 being the poorest quality. The resultant effect of our cardiac study and expert consultation yielded an objective consideration where we defined 12 subjective criteria for all the cardiac frames, and we defined 4 objective quality standards for all the cardiac frames as well. The next thing we did was to define our artificial intelligence assisted assessment method. This will make use of deep neural network, a combination of deep neural network and LSTM, long short-term memory. Let me quickly talk about our attributes. The first attribute is the on-axis visibility. It has its clinical relevance to linear measurement, volumetric computation, ejection fractions. It also has a pathological significance. The next attribute is the left ventricle clarity. We're able to measure the RMS contrast of dissimilar anatomical features within an image. The next one is the depth gain, which measures the intensity of discrete signal sample at a given region of interest. We understand that there are embedded tissues in the apical section as well as the basal section of the image. So depth gain measure the near field angle and far field angle and make all the tissues distinguishably recognized. The last of our attributes is the foreshortening. In foreshortening, it has a clinical relevance to quantifications, measurement, and diagnosis. And finally, is our deep learning model, which consists of 4 different architectures. Each of the architectures had to elicit the prediction score for on-axis, clarity score, depth gain score, foreshortedness score, respectively. Our model was evaluated, and we have an overall accuracy of 97.6%. What is the big deal? The big deal of our research is the impact it creates in the secondary care within the health sector. For the first time, we are able to establish a novel interrogation method on quality assessment of cardiac frames. We are also able to present a coherent and clinically relevant standards for objective assessment of 2D image quality. It provides a real-time feedback and a guide for operator to acquire optimum quality images. And it gives accurate quantifications and reliability in diagnosis. Also, it eliminates industrial shortages in expert supply and allows a better trigger response to patient health care. The biggest part is the reduction of mortality rate, 17.9 million per year, according to WHO. We believe this will be reduced significantly. And finally, it opens doors to a range of possibility in automated cardiac diagnosis. On this account, I want to end my presentation, and I want to thank everybody for listening.